A very warm welcome to all of you. Today is the last lecture of this course on power quality problems and solutions. This is lecture number 42. I should write here lecture number 42. And this is the continuation of our discussions on improved power quality AC to DC converters. We have been discussing improved power quality AC to DC converters over last two lectures, and this is the third lecture in continuity with that. In our last lecture, in fact last two lectures, we have discussed about improved power quality AC to DC converters. In lecture number 40, we first discussed single phase unidirectional AC to DC improved power quality converters, and the prominent among them that we discussed in our class were single phase unidirectional buck converter, single phase unidirectional AC to DC boost converter, similarly single phase unidirectional AC to DC buck boost converter, and we also discussed single phase unidirectional AC to DC flyback converter. And in those improved power quality AC to DC converters, we have seen that the converter, that is the DC to DC converter, which is connected to a rectified AC line through bridge rectifier, the converter operates in discontinuous conduction mode of operation. And operating in DCM, discontinuous conduction mode, gives such converters self-power factor correction property, which means that you don't need any current loop for controlling the line current or source current. The current drawn by the converter will automatically follow the sinusoidal pattern. No doubt it will be in the form of a large number of pulses in both positive half and negative half cycle. But if you put a small high pass LC filter, that will make currents purely sinusoidal and in phase with the voltage. Right? Why they are called unidirectional AC to DC converters? Because diode bridge rectifier on the front end blocks the reverse flow of current, so that current can flow in only one direction and there is power flow only from source to the load. The reverse power flow from load to source is not possible in such a converter. Then in previous lecture, lecture number 41, we discussed a special type of single phase PWM pulse width modulated AC to DC converter, which is also a category of buck converter. It produces average output voltage, which is always less than peak input voltage, but it's a bidirectional buck converter. Unlike the unidirectional AC to DC buck converter, this PWM AC to DC converter is a bidirectional buck converter. Okay, the power can flow in both the directions from source to load if load is a DC machine and if machine operates in the motoring mode. And power can flow in the reverse direction, that means from load to source, if the same machine operates in the generating mode and regenerates the energy and supplies that energy back to the source. We had a comprehensive discussion on this type of converter. I discussed with you in the last lecture how to develop the control algorithm, pulse width modulation technique. I discussed with you PWM technique, how control pulses using PWM technique can be generated, and how with the help of waveforms we try to understand the operation of converter, PWM converter, in both rectification and as well as inversion modes of operation. Now in today's lecture, I'm going to first discuss with you, I will write here single phase unidirectional boost converter. Boost converter. We have already studied single phase unidirectional boost converter, but that boost converter was operating in discontinuous conduction mode. Now today we will again study single phase unidirectional boost converter, but in CCM. CCM means continuous conduction mode of operation. Okay. Before I discuss with you single phase unidirectional boost converter, let me draw, for your reference, again draw the power circuit diagram of a DC to DC boost converter. A DC to DC boost converter looks like this. All of you must be knowing about this configuration. This is a DC to DC boost converter. Load voltage is say V0 and load current is I0. The switch will have two states, on state and off state. Okay, if you see the control pulses, these are the control pulses for the switch, say control voltage VC. This is 0 dTs, where D is the duty ratio and Ts is the time period, and this is Ts. These are the control pulses. Total time period is Ts, as you can see, and switching frequency of course will be 1 by Ts, and generally the switching frequency of this converter or of this switch is of the order of kilohertz. Now when control pulse is high to this switch, it turns on and current flows in this direction. Your load gets disconnected from the source because source is shorted by this switch through the inductance, boost inductance, and current flows in this direction on the input side. And voltage across inductor will be like this. Positive voltage, and inductor will store the energy. And when inductor stores the energy, what happens to the current through the inductor? It increases. So it increases from some minimum value to maximum value. Then from DTS to TS, the control pulse or gating pulse to the switch, which may be an IGBT, it is off, it is low. Therefore, IGBT turns off. As soon as IGBT turns off, the voltage across the inductor reverses and inductor releases all the stored energy, and that energy flows into the output stage. A part of that energy is used for charging the capacitor, and rest of that energy is used for supplying the load. And when that happens, that means when the inductor is releasing the energy, we already know the current through the inductor decreases, because inductor has to force current against a higher voltage. Since this is a boost converter, the output voltage is greater than input voltage, and when the inductor has to force current against a higher voltage, which is across the capacitor, the current decreases. So when there are two time intervals, therefore one is energy storage interval. Energy storage interval, and that energy storage interval is from 0 to dTs, and during this energy storage interval, S is on. This is the energy storage interval 0 to dTs. Switch S is on, and when switch S is on, equivalent circuit is like this. Switch is on, this is the equivalent circuit, and this freewheeling, this diode, not the freewheeling diode gets reverse biased, and this is the capacitor, and this capacitor supplies energy to the load during this energy storage interval. Now why is this called energy storage interval? Because the current flows on the input stage, like in the input stage like this. Let's call this current as IS, and therefore energy in the inductor stores, energy gets stored in the inductor because of flow of this current in the path like this. That's why it's called energy storage interval, and during this interval the current through the inductor keeps on increasing. And then at DTS, the control pulse is made low. From DTS to DTS, the control pulse is low, and when control pulse is low, the inductor releases the energy. So that is called energy transfer interval. Energy transfer interval. And energy transfer interval is from DTS to TS. That is DTS less than or equal to T, less than or equal to TS. And during this energy transfer interval, switches off, equivalent circuit is like this. This is your DC input. This is inductor L, voltage across the inductor reverses and it supplies energy. Diode ab conduct karega, diode is on. This is the capacitor C, and this is the load. Part of this current goes into the capacitor, so it charges the capacitor, and rest of the current goes into the load and it supplies energy to the load. Okay, so this is called energy transfer interval. So in the energy transfer interval, the inductor releases the energy, stored energy, which it had stored in the previous. Okay. So therefore, what will happen to the current through the inductor? It will decrease, and then there will be again energy storage interval, energy releasing interval, and so on. So therefore, this will be the current which will be flowing on the source side or inductor current. It will be rising from minimum value to maximum value during energy storage interval, and it will be falling back from maximum to minimum value in the energy transfer interval, like this. Now in our case, our converter is not a DC to DC boost converter, it is an AC to DC boost converter. Now operating in continuous conduction mode of operation. Now when I say it is an AC to DC boost converter, then it's actually AC to DC boost converter is comprising of a DC to DC boost converter which is connected to rectified AC. That means on the AC side you have a bridge rectifier, diode bridge rectifier like this, which is a front end rectifier. और ये आपकी source voltage है, this is the source voltage, and this is the boost inductance, और यह आपकी source current IS है. This is the connection, and then you have the switch, which may be an IGBT operating at a very high switching frequency. You have a diode, fast recovery diode, and on the output stage you have a capacitor C, and you have a load resistance R. The voltage across the load is plus minus V0, and current through the load is I0. So this is single phase unidirectional AC to DC boost converter. Boost converter. Why it is unidirectional? Because energy can flow only, power can flow only from AC source to DC load, AC side to DC side. Reverse flow of power is not possible in this case. Now its operation is very simple. This is your source voltage, for example Vs. Okay. Now again you have two intervals of the switch, energy storage interval and energy transfer interval of the converter. In the energy storage interval from 0 to DTS, switch is closed. That means it is on. And when switch is on, आपकी output stage disconnect होती है input stage से, because this diode gets reverse biased. And capacitor at the time supplies some energy to the load. So load gets power supply or energy from the capacitor. And what happens when this switch is on? Current flows through this diode and then through this switch like this, or positive half cycle. And for negative half cycle, current again flows through this diode, switch and back. Okay, let us take positive half cycle of source voltage. Positive half cycle of source voltage means this is plus, this is minus, plus minus. So this pair of diode triggers, they conduct, and current flows like this. And since switch is closed, instead of going to the output stage, it is bypassed by this current flows through the switch और वापस यहाँ से इस diode से. So therefore current through the inductor increases. If I show current through the inductor for positive half cycle, current through the inductor increases. And as soon as it reaches some value, the switch is turned off. That means energy transfer interval comes, which is DTS to TS. During this period, switch is off. Control pulse to the switch gate is made low and it turns off. As soon as this switch turns off, now it is time for this inductor to release the energy. And when inductor releases the energy, इसके across voltage plus minus हो जाती है, उससे ये diode forward bias हो जाता है, and it releases the energy like this. Diode D1 conducts. Then current cannot flow now through the switch because switch open हो गया है, off है. It will flow through the output stage. Some of this current will go into the capacitor and rest of the current will be taken by the load as per the power rating of the load. Or return path through this diode होगा. So therefore inductor is releasing the energy like this. And when inductor releases the energy, what happens to the current? Current at that time decreases. Current decrease हो जाती है. इससे पहले कि ये zero हो जाए. Next energy storage interval comes. I mean switch is again turned on. When switch is turned on, current again flows through the switch like this and current through the inductor increases. And then there is energy transfer interval. Current decreases. So it goes on like this. It follows this voltage. अब डीसी टू डीसी कन्वर्टर में करंट ऐसे थी, स्टेडी स्टेट करंट. I mean, it had an average value. It was neither increasing nor decreasing. लेकिन इस केस में ये साइनोसाइडली इंक्रीज हो जाएगी और साइनोसाइडली डिक्रीज हो जाएगी, because at each instant the instantaneous value of voltage is changing. I mean, what is the voltage at this point? It is minimum, and then when next switching occurs here, the applied voltage is higher. So therefore, higher current flows. When next switching takes place here, the voltage, applied source voltage, has already increased, so that results in higher current. तो करंट therefore constant magnitude पे नहीं फ्लो होगी, ये वोल्टेज के साथ राइज होती जाएगी. And when voltage falls, the current also falls like this. This is for positive half cycle. Same thing will happen during negative half cycle. This is 0, pi, 2 pi. In the negative half cycle also, current will sinusoidally increase and sinusoidally decrease. So this is the source current, IS. Now the question is, when the source current is during the energy storage interval, source current is rising, and during the energy transfer interval, it is falling. So therefore the current is having, no doubt it is following a sinusoidal pattern. It is following the voltage, that is sinusoidal pattern, but it has got ripples. It is increasing, decreasing, then again increasing, decreasing. So because of this increase and decrease, there are ripples. You can see here ripple content hai current mein. Now how much ripple will be there? That will be decided by hysteresis band. So what you will do, you will use a pulse width modulation technique, which is called hysteresis current control technique. Hysteresis current control, that is HCC technique. In hysteresis current control technique, what we do, for example, we generate a reference current. हम क्या करते हैं, हम एक reference current positive half cycle में भी generate करते हैं और negative half cycle में भी. Suppose this is reference current IS star, source current, which is purely sinusoidal in nature, which is equal to Im sin omega t. Now you can see this reference current is purely sinusoidal in nature. Then we create a band, upper hysteresis, that's called upper hysteresis band, around this current like this. इस band की gap है plus h, और नीचे से भी हम lower hysteresis band create करते हैं. इसकी भी height है h. Then what you do, you cause the, for example, when you are here, switch is turned on, energy storage interval is there, switch is turned on for some time, and current flows like this through the switch, and energy in the inductor gets stored. And what will happen to the current? Current through the switch or current through the inductor rises. Source current rise हो जाती है. As soon as source current का upper band UP, that is equal to I reference IS star plus H. Similarly, source current जो lower band पे होगी, IS LO lower, that is equal to IS star minus H. So what happens? I will repeat. Control pulse is issued at the gate of this power semiconducting device, which may be a power MOSFET, a power transistor, or say an IGBT, and it immediately turns on, and then current flows like this. And therefore, energy gets stored in the inductor. That's why it's called energy storage interval. And what will happen to the current, source current through the inductor, which is also source current? It rises. It starts rising. But as soon as it touches the upper band, this is called upper hysteresis band. I will write here upper hysteresis band. और ये जो है ये lower hysteresis band है. Upper hysteresis band is equal to IS star plus H. As soon as it reaches IS star plus H, that's upper hysteresis band, your control logic circuit will withdraw the control pulse from the gate of this device, and device automatically turns off. और जो ही device turn off हो जाता है, inductor now releases the energy, stored energy, and when it releases the energy, current flows like this. It cannot flow through the switch because switch is now off. it has to flow into the output stage. Some of this current goes into the capacitor and charges the capacitor, and rest of the current flows through the load and back. So therefore, energy gets transferred to the output stage. That's why this interval is called energy transfer interval. And during this energy transfer interval, what will happen to the current? Current decreases. तो ये current decrease हो जाएगी. अब जो ही ये lower hysteresis band को touch करेगी, which is IS star minus H, your PWM controller will again issue, और आपका hysteresis current controller जो है HCC, it will again turn on the switch. It will issue control pulse at the gate of the switch. Switch फिर से turn on हो जाएगा और फिर से एनर्जी स्टोरेज इंटरवल आ जाएगा और करंट फिर से राइज होगी और उसके बाद फिर से फॉल होगी. सो इट विल फॉलो रेफरेंस करंट. दिस इज योर एक्चुअल सोर्स करंट IS, and it follows reference source current IS star very closely within the hysteresis band. अब आप यहाँ पूछ सकते हैं कि आपकी रेफरेंस करंट तो ऐसे है, लेकिन आपकी एक्चुअल करंट तो उसमें तो काफी ज्यादा रिपल है. I agree with you. It has high ripple because for the sake of understanding, for the sake of explaining to you, I had to make this hysteresis band very large. ताकि आपको ये करंट प्रॉपरली इसका ऑपरेशन ताकि आप समझ जाए. लेकिन एक्चुअल प्रैक्टिस में hysteresis band इतना बड़ा नहीं होता. Hysteresis band is very very small, very narrow. That means if this is your reference current, say positive half cycle में 0 से pi तक, if this is reference current IS star, आपकी actual current का hysteresis band बहुत छोटा होगा, and it will very closely follow this reference current. आपकी actual current IS will be very nearly equal to IS star. Hysteresis band बहुत छोटा होता है. It's not we don't have a very large hysteresis band. Hysteresis band is very very narrow, very narrow. It is so narrow that you may not be able to differentiate between actual source current and reference source current. No doubt there will still be ripples, but these ripples will be very very small. So therefore, your actual current will be very closely following the reference current, and since your reference current is sinusoidal and it is in phase with source voltage, आपकी actual current भी sinusoidal होगी और in phase with source voltage होगी. So that will make your single phase bidirectional boost unidirectional boost converter a linear load. Why linear load? Because the current is drawn by this converter is almost purely sinusoidal, nearly sinusoidal, and it is in phase with the voltage. So the converter is not drawing any reactive power. Power factor is equal to unity, 1.0. Input power factor is unity. This is how a single phase unidirectional boost converter works. Now, अब आप यहाँ देख सकते हैं, why is it called continuous conduction mode of operation? Because आपकी inductor current जो है, which is also your source current, unidirectional boost converter जो आपने last to last lecture में study किया, where single phase unidirectional boost converter was operating in discontinuous conduction mode of operation, उसमें source current या inductor current ऐसे थी, discontinuous. It was discontinuous. But here current is continuous. It's not becoming zero at any point. It is very closely following the reference current and it is continuous. That's why it's called continuous conduction mode of operation. And in that case, since current was, in the form of pulses, you needed a small LC filter on the input side. एक filter चाहिए होगा ताकि ये current, इस current में से high frequency harmonics निकल जाए और ये sinusoidal बन जाए. You don't need that filter in this case. Your current is already almost nearly sinusoidal. It's not in the form of pulses. So this is the advantage of continuous conduction mode of operation over discontinuous conduction mode of operation. But the problem with continuous conduction mode of operation of a single phase unidirectional boost converter is that you need a current control loop for making this current, continuous and sinusoidal. To understand that, let me explain that with the help of schematic diagram of hysteresis current control technique, जो आप HCC technique इसमें use करते हैं, which is also a type of PWM method. It's also PWM, pulse width modulation technique. Let me explain to you that in details. This is your single phase unidirectional boost converter power circuit diagram. Let me draw it first. यह आपका स्विच है, लेट अस से IGBT. Okay. Switch S, and this is fast recovery diode. This is output side capacitor, output stage capacitor, and this is load resistor R. Load voltage is plus minus VDC or V0, and load current is I0. And here you have AC source voltage. I have a current sensor. Current sensor मैं क्यों use कर रहा हूँ, I will tell you in a minute's time. This is your source current, IS. This is the connection. Okay, this is the power circuit diagram of single phase unidirectional boost converter. Now, aim is to make the source current sinusoidal and in phase with the voltage. That means if your voltage is this is source voltage, your source current should be sinusoidal like voltage, and it should be in phase with the voltage. How to achieve that? And simultaneously, other control objective in this case is to maintain the DC bus voltage or output voltage constant. आपके output voltage V0 है, which is the same voltage जो इस capacitor के across voltage है. What we do, we put a voltage sensor. एक voltage sensor capacitor के across लगाते हैं. It senses the output voltage. और आपकी output voltage है say V0. So whatever is the voltage across capacitor, that is your load voltage. So this is sensed load voltage or measured load voltage. Simulation में आप, you will use a current measurement block which acts as a voltage sensor. And in actual practical circuit, you will use a voltage sensor. A voltage sensors, Hall effect voltage sensors are readily available in the market, and that voltage sensor will sense the voltage across capacitor. That means it will sense the output voltage. And then this output voltage is compared in a comparator with a reference output voltage V0 star. Let us suppose the reference output voltage, let reference output voltage, that is the desired output voltage, be say 300 volts. Suppose input voltage, let output voltage, reference output voltage be, let us say 400 volts. If your input voltage is 230 volts RMS value, uska peak hai 325 volts. And in a boost converter, the average output voltage should be greater than peak input voltage. Input voltage ka peak 325 volts hai, so let us say output voltage, desired output voltage is 400 volts. So it is greater than peak input voltage. It's just an example. It can be even more than 400 volts. It depends upon aapki load voltage requirement kitni hai. Let us suppose our desired or reference output voltage across the load is 400 volts. So this is V0 star, this is V0. And when you connect the load across the capacitor, the capacitor will start supplying power to the load. I mean, when the switch is on, energy storage interval is there, and there is no energy flowing into the output stage, and load gets energy from capacitor. As a result of that, capacitor discharges. I mean, when capacitor is supplying this load current, capacitor starts discharging, and the voltage across capacitor, that's output voltage, falls. It becomes less than V0 star, और एक error आ जाता है EV0. What is this error EV0 equal to? It is reference voltage V0 star minus actual voltage. Since actual load voltage has become less than reference load voltage, an error will be produced. Then this error will be processed in a PI voltage controller. I will write here PI voltage controller. It's a PI controller. What's the job of PI controller? To make this error equal to 0. And this error will be equal to 0 only when actual load voltage is same as reference load voltage. That means when this capacitor gets charged again and its voltage comes back to its reference value of 400 volts. How can we achieve that? The output of this PI voltage controller will be peak of the reference current. Okay? अब reference current कैसे हम generate करेंगे? Our reference current should be like this. This should be our reference current, and our actual current within the hysteresis band should follow this reference current. And this reference current, let us call this IS star. It should be Im sin omega t. IM तो यहाँ PI वोल्टेज कंट्रोलर का आउटपुट पीक वैल्यू ऑफ करंट देगा, and that has to be multiplied by sine omega t. Sine omega t is a unit vector where from we get it, and this reference current should be in phase with the source voltage. So therefore you can derive this sine omega t unit template from the source voltage itself. How? By connecting a voltage sensor across the source. आपकी जो सोर्स वोल्टेज है इसको सेंस कर लीजिए बाय वोल्टेज सेंसर से, तो ये आपका वोल्टेज सेंसर है, ठीक है. सो इट इज सेंसिंग द वोल्टेज एंड देन you multiply it by a gain of 1 by Vm. So what is Vs? Vs is Vm sin omega t, we already know. इसको हम multiply कर रहे हैं gain of this, it's a gain block, और इसका gain कितना है 1 by Vm. Vm is the peak of source voltage. Vm and Vm cancels, so this is equal to sin omega t. So therefore यहाँ से इसका आउटपुट हमें sin omega t मिलेगा, और जब हमें sin omega t मिलेगा वो हम एक प्रोडक्ट ब्लॉक में देंगे. ये हमारा यूनिट वेक्टर टेम्पलेट है sin omega t. We are multiplying that by Im. So Im into sin omega t becomes Im into, in this product block these two get multiplied, it becomes Im into sin omega t, which is equal to your Is star, reference current. Your reference current therefore is purely sinusoidal in nature, and it is in phase with the voltage, because this sin omega t we have actually got from the source voltage itself. So therefore आपकी जो reference current है वो purely sinusoidal है, and it is in phase with the source voltage, और इसका peak value that will be determined by this PI voltage controller. What does that mean? Suppose आपका capacitor, suppose your capacitor is supplying energy to the load during energy storage interval, and during that period capacitor discharges, इसकी voltage कम हो जाती है, drop हो जाती है, and error आ जाता है. PI voltage controller processes this error, and at its output it gives a control signal Im. Im we are multiplying by sin omega t, so your reference current becomes Im sin omega t. ये आपकी reference current बन जाती है Is star equal to Im into sin omega t. This is given to a hysteresis current controller, which is a PWM controller. Hysteresis current controller looks like this. Symbolically it looks like this. Yeah, ऐसे होता है. This is your HCC block, hysteresis current controller block. इसका एक इनपुट Is star है जो हमने यहाँ से डिराइव किया, और दूसरा इनपुट इसकी एक्चुअल सोर्स करंट है Is. This is the second input Is. So what it does, ये एक्चुअल सोर्स करंट को Is star के साथ कंपेयर करता है, और इस हिस्टेरेसिस करंट कंट्रोलर में ऑलरेडी आपने एक हिस्टेरेसिस बैंड बनाया होता है. इट्स वन इनपुट इज Is star, सो दिस इज Is star. ये इसके ऊपर और नीचे बैंड बनाता है, हायर हिस्टेरेसिस बैंड और लोअर हिस्टेरेसिस बैंड, और अकॉर्डिंगली यहाँ से कंट्रोल पल्स मिलती है. दिस इज द कंट्रोल पल्सेस टू स्विच S टू S. वो स्विच में जाती, स्विच के गेट पे जाती है. I can show this control pulse connected to the gate. ये गेट पे जाती है, इससे आपके स्विच की टर्निंग ऑन एंड टर्निंग ऑफ हो जाती है. फॉर एग्जाम्पल, if your source current is 0, so it puts the switch into the on state. It makes the gate pulse high at the gate of the switch. आपका switch on हो जाता है, current rise हो जाती है. But within the hysteresis current controller, the mechanism is such that as soon as this current reaches upper hysteresis band, it makes the control pulse low automatically and switch off हो जाता है. और जब switch off हो जाता है, energy gets transferred to the load, और उससे current decrease हो जाती है. और जब ये lower hysteresis band को touch करती है, फिर से ये switch को on off ऐसे करता है. तो आपकी अगर reference current ये है, आपकी actual current within very narrow hysteresis band, it follows this reference current. And since your reference current is in phase with the voltage, your actual source current Is is also in phase with the voltage, giving unity input power factor. So therefore your Is is Im sin omega t. ये sinusoidal waveform बनती है. Im is the peak value. अगर आपका कैपेसिटर ज्यादा डिस्चार्ज हुआ तो Im का मैग्नीट्यूड यहाँ बढ़ेगा, और that means the converter will draw large current from the source, क्योंकि Im बढ़ गया. Im, which is the PI voltage controller output, agar ye, if this error is more, I mean if there is a more drop in the output voltage because of high load, V0 is much less than V0 star, IM will increase. उससे रेफरेंस करंट की पीक बढ़ेगी. अगर पहले रेफरेंस करंट की पीक थी वो अब बढ़ेगी. That means more current will be, and since your actual current is following the reference current, so more current will be drawn by the converter from the source, and that extra current will charge the capacitor, and it will bring capacitor voltage or output voltage back equal to V0 star, making error EV0 equal to 0. Right? और अगर आपकी आउटपुट वोल्टेज एरर कम है, V0 इज लेस देन V0 स्टार, लेकिन अब डिफरेंस ज़्यादा नहीं है, तो IM का मैग्नीट्यूड कम हो जाएगा. उससे सोर्स से जो करंट आएगी वो कम करंट आएगी, बिकॉज यू डोंट नीड लार्ज चार्जिंग ऑफ द कैपेसिटर. दिस इज हाउ योर hysteresis current control mechanism works. You can simulate this converter in MATLAB Simulink SimPower System software. It's very easy. I have already done it. I can discuss it with the interested students in any of the simulation classes. So this is how it works. What I was telling you that now if this is your source voltage, Vs 0, pi, 2 pi, this is the reference current, and of course this is the actual current, source current. Source current is following the reference current, and since reference current is sinusoidal and in phase with the voltage, your source current, since it follows the reference current very closely, it is also sinusoidal and in phase with the voltage. So therefore your unidirectional boost converter looks like a linear load to your source, because it is drawing purely sinusoidal current and it is not drawing any reactive power. Why? Because input power factor is unity. Current is absolutely in phase with the voltage. In this case, you don't need the filter, because your current is not in the form of pulses. It is a continuous current. But you need a current loop in this case. For continuous conduction mode of operation using hysteresis current control, you need a current loop. ये देखिए, आपको एक current loop चाहिए. You have reference current IS star, and you have to sense the actual current IS, compare the two in the hysteresis current controller, and that will generate the control pulses for this thyristor. So you need a loop, current loop. In other words, this current is programmed in such a way that it very closely follows the reference current. And this current loop is not required when the same boost converter is operating in discontinuous conduction mode of operation. We don't need these current sensor, current loop there. There, your converter draws this type of current, discontinuous current, and by putting a small LC filter, it will make current sinusoidal. Okay. So another problem, okay, that is the difference between discontinuous conduction mode of operation and continuous conduction mode of operation. If you are removing the load, agar load nahi hai, you are removing the load, then in that case, you don't need to transfer any energy to the output stage. Why? Because when you are transferring energy to the output stage, that energy, basically a part of that energy is consumed by the load, and some energy charges the capacitor. If you are removing the load from the, if there is no load across the converter output, so no energy should be transferred. But if your hysteresis current controller is working, during energy storage interval, energy gets stored in the inductor, and during energy transfer interval, it transfers the energy. And since there is no load to take that energy, all the energy will be dumped into the capacitor. Usse kya hoga? Capacitor ki voltage बढ़ती जाएगी, and it will become dangerously large voltage, and it may damage the capacitor, and it may damage your circuit also. So therefore, this system has to be a closed loop control system. Single phase unidirectional boost converter using hysteresis current control technique, when it is operating in continuous conduction mode of operation, it cannot be an open loop control. If it is an open loop control, then you will be, even if there is no load, you will be continuously transferring the energy to the output stage. But since there is no load, all that energy will get dumped into the capacitor, and that will gradually increase the capacitor voltage, and capacitor may get bursted because of very high voltage. Dangerously high voltage will appear across the load. But if it's a closed loop system like this, अगर आपका लोड खत्म हो जाता है, तो आपकी ये आउटपुट वोल्टेज इनपुट वोल्टेज के बराबर हो जाती है, एरर 0 हो जाता है, So there is no hysteresis current. I mean, no energy will be transferred to the output. That means switching frequency will be zero. Switching frequency zero means the switch will not, the power semiconductor device will not switch at all, because it doesn't have to transfer any energy to the output stage. Why? Because load has got disconnected. But as soon as you connect the load, then the switching operation will take place. The switch will turn on and turn off, then again turn on, turn off. There will be energy storage and interval and energy transfer interval within the hysteresis band. Your current will be following reference current within the hysteresis band. And one drawback of hysteresis current control is that the switching frequency is not constant. It is a variable switching frequency. If your load parameters change, I mean load value changes, the switching frequency of the switch also changes. Okay. And sometimes the switching frequency becomes very, very large. And another thing I want to tell you about the hysteresis band is that how do you decide about hysteresis band kitna hona chahiye? If your hysteresis band is high, I mean large hysteresis band. If hysteresis band is large HB, then your source current may become like this, something like this. No doubt it may be following sinusoidal pattern, but ripple content in the current will be very large, and THD of the current will be much greater than 5%, which is unacceptable. On the other hand, if your hysteresis band is low, I mean lower hysteresis band, your source current may almost look like reference current. You may not be able to see these ripples there. But the hysteresis band has to be very narrow. Narrow hysteresis band means high switching frequency operation will take place. अगर hysteresis band ये है तो इसमें ऐसे switching होगी. अगर hysteresis band आप narrow करते हो तो इसमें quick switching होगी. जहाँ पे ये 1 cycle complete करता है वहाँ ये 10 cycle complete करेगा same time period में. So narrower the hysteresis band, higher is the switching frequency, and how narrow the hysteresis band can be, that will be decided by the type of device you are using. If you are using power transistor, you cannot go more than a few kilohertz. If you are using power MOSFET, you can go up to 100 kilohertz. Then you can have very narrow hysteresis band. If you are using IGBT, you cannot go more than 10 kilohertz. So the type of device and switching power losses will tell you what should be the hysteresis band. So therefore hysteresis band should neither be very large nor very small. You have to make a compromise between the two. Okay, so that is about single phase unidirectional boost converter operating in continuous conduction mode of operation, and I have shown you the closed loop operation using hysteresis current control technique, HCC technique. Again, why it is unidirectional boost converter? Because current can flow only in this direction. Reverse flow of current is not possible because of this bridge rectifier, diode bridge rectifier. This diode bridge rectifier blocks currents in the reverse direction. So therefore power can flow only in one direction from source to load. Reverse flow of power is not possible. Okay. Another variation of this is like this. This single phase boost converter can be, another variation is like this. It could be something like this. Let me first of all draw the power circuit diagram, then I will explain. This is source voltage Vs, this is inductance L, this is source current Is, this is the output capacitor C, and this is the load, or load voltage is V0 and load current is I0. So this is switch S1, S2, and anti-parallel or feedback diodes are D1, D2, and let this diode be D3 and this diode be D4. This is also a single phase unidirectional boost converter operating in continuous conduction mode of operation. Operation is very simple. First of all, I will discuss with you energy storage interval. Energy storage interval, that is 0 to dTs. During this period, what will happen? Switch S1 will be on. S1 will be given control pulse at its gate, it will turn on. Let us take positive half cycle of source voltage. Let's take positive half cycle of source voltage. During the positive half cycle of source voltage, this terminal A is positive with respect to this terminal B. I mean, this is plus, this is minus, so this is plus, this is minus. And when control pulse is given to switch S1, current will flow like this. This is energy storage interval. So switch S1, or instead of current going here, अगर current यहाँ जाएगी तो यहाँ से फिर वापस भी आना है, but there is no path. Why there is no path? Because diodes always conduct from anode to cathode. They cannot conduct from cathode to anode. Current वापस आने का मतलब हुआ या तो यहाँ से जानी चाहिए cathode to anode या यहाँ से. But current in a diode cannot flow from cathode to anode. Therefore, जब ये switch up on करते हैं, the current will flow through switch S1, or instead of going here, it will complete its path through D2, D2 के through, or ऐसे. So equivalent circuit, let me draw the equivalent circuit for you. Equivalent circuit will look like this. This is positive half cycle of source voltage. Current is flowing through the inductance. It will first of all flow through switch S1. ये आपका switch S1 है. Switch S1 on हो गया, and then return path will be through D2. ये देखिए, return path is through D2, और ये वापस जाएगी. It will go back. So current will flow like this. And since current is confined in this path, at that time capacitor supplies energy to the load. The output stage is disconnected from the input stage, and load gets energy from the capacitor because capacitor was previously charged for a very small period of time, maybe a few microseconds. And since current flows like this, the current through the inductor increases like this. And this is energy store interval, and energy gets stored in the inductor. After that, what will happen? Your hysteresis current controller will withdraw control pulse from switch S1. So S1 will turn off. So we have next interval then, energy transfer interval. What will happen in the energy transfer interval means dTs to Ts. S1 ऑफ हो जाता है क्योंकि इसकी कंट्रोल पल्स लो हो जाती है. हिस्टेरेसिस करंट कंट्रोलर विल टर्न इट ऑफ. और जब ये ऑफ हो जाता है, इंडक्टर के अक्रॉस वोल्टेज रिवर्स हो जाती है, उससे ये डायोड फॉरवर्ड बायस हो जाता है, एंड करंट फ्लोज थ्रू डायोड D3, देन थ्रू लोड. कुछ करंट कैपेसिटर में जाएगी, कुछ लोड में, और वापस कहां से आएगी? वापस D2 के थ्रू आएगी ऐसे. एंड सिंस नाउ द सोर्स हैज टू फोर्स करंट against a higher voltage, because boost converter में output voltage input voltage से high होती है, current will decrease. And since inductor is releasing the energy, we know when inductor releases energy, current decreases. Current decrease हो जाएगी. And equivalent circuit, let me show you the equivalent circuit during energy transfer interval. It will be like this. यह आपका इंडक्टर है, यह आपकी सोर्स करंट है. D3 conducts, and then capacitor, इसमें कुछ करंट जाती है और कुछ लोड में जाती है, लोड रेजिस्टेंस में, और वापस रिटर्न पाथ इज थ्रू डायोड D2. So current flows through D3, then output stage D2 के through वापस. And as soon as current, this is upper hysteresis band, this is lower hysteresis. As soon as current touches the lower hysteresis band, then switch S1 is again turned on. So therefore आपका positive half cycle कुछ इस तरह हो जाता है, on off. And your actual source current from 0 to pi very closely follows the reference source current, which is purely sinusoidal. Okay, this is what happens in the positive half cycle. Let's see what happens in the negative half cycle of source voltage. Negative half cycle of source voltage. Negative half cycle of source voltage में this terminal will become positive with respect to this. इसका मतलब ये B positive हो जाएगा, A negative हो जाएगा, and इसमें भी energy storage and energy transfer interval है. Energy storage interval. Energy storage interval is 0 to dTs. What happens in this energy storage interval? Now your hysteresis current controller will not issue any control pulse to S1. It will, during negative half cycle, it will issue control pulse to S2. So S2 को control pulse मिलती है, ये on हो जाता है. As soon as S2 turns on, since ये terminal positive है, current ऐसे flow होती है. So S2, it will not go here क्योंकि यहाँ से path नहीं है. It will flow through S2 और return D1 के through वापस आएगी. So therefore equivalent circuit, I will write here equivalent circuit. Equivalent circuit will be like this. ये L है. See ऐसे ये पॉजिटिव टर्मिनल है सोर्स वोल्टेज का. S2 ऑन हो रहा है. So S2 is turning on और रिटर्न पाथ D1 के थ्रू हो रहा है. दिस D1 भी ऑन हो रहा है वापस. So current flows in then. This is the direction of current. It is negative. So therefore what will happen? Current rise हो जाएगी. And as soon as it touches the upper hysteresis band, energy transfer interval शुरू हो जाएगा. That means S2 off हो जाएगा. आपका hysteresis current controller इसको off करेगा. So energy transfer interval शुरू हो जाएगा. Energy transfer interval, and energy transfer interval is dTs to Ts, time period Ts. So S2 off हो जाता है because gating pulse at the gate of this switch is low. It's made low by hysteresis current controller. जब ये off हो जाता है, so inductor current तो ऐसे flow हो रही है, so inductor के across voltage reverse हो रही है. अब current is reverse. It has to release the energy. इसकी release जब करेगा S2 के through, now current cannot flow क्योंकि S2 off हो गया. So this is the path. The current will flow through D4, then output stage, वापस D1 से आएगा. So equivalent circuit will be like this. Let me draw the equivalent circuit. Negative half cycle of source voltage is there. This is boost inductance. See what happens. Diode D4 on हो जाएगा. देखिए D4 on हो गया. ये फिर आउटपुट स्टेज है. कुछ करंट कैपेसिटर में जाएगी, इसको चार्ज करेगी, कुछ लोड में जाएगी, और करंट वापस कैसे आएगी? करंट यहाँ इट हैज फ्लोन थ्रू D4, D1 के थ्रू वापस पाथ कंप्लीट करेगी. D1, एंड सिंस D1 इज कनेक्टेड टू दिस, तो वापस ऐसे फ्लो होगी. नाउ सिंस इंडक्टर इज रिलीजिंग द एनर्जी, व्हाट विल हैपन टू करंट? करंट अब डिक्रीज हो जाएगी. उसके बाद फिर से एनर्जी स्टोरेज एलिमेंट, और फाइनली आपकी नेगेटिव हाफ साइकिल में करंट ऐसे आएगी. इट विल आल्सो बी साइनोसॉइडल. इट विल बी वेरी क्लोजली फॉलोइंग द रेफरेंस करंट. दिस इज हाउ things happen. So this is another topology of single phase unidirectional boost converter. In the previous topology, we had a diode bridge rectifier and one switch. In this case, we don't have a bridge rectifier. We have two power diodes and two self-commutated power semiconducting devices like IGBTs. And it works in the same way as your other configuration that we have studied few moments back. So this is also, this is another variation of single phase unidirectional boost converter. Can we have single phase bidirectional boost converter? The answer is yes. We can have a boost converter which is bidirectional in nature. Just like in previous class we have studied bidirectional buck converter, PWM converter. Here also boost converter, we have already studied unidirectional discontinuous conduction mode as well as continuous conduction mode using hysteresis current control technique, HCC technique. Now we can have single phase boost converter which is bidirectional. I am going to discuss with you that single phase bidirectional, that is BD boost converter. Single phase bidirectional boost converter. Of course, continuous conduction mode of operation I am discussing with you. Power circuit diagram of that single phase bidirectional boost converter will be like this. Let me draw the power circuit diagram first. Then I will explain its operation. This is the power circuit diagram of a single phase bidirectional boost converter. All the four switches may be IGBTs or power MOSFETs or power BJTs or GTOs, self-commutated power semiconducting devices, maybe IGBTs. So this is S1 with feedback diode D1. This is switch S2 with feedback diode D2. This is switch S3 with feedback diode D3, and this is switch S4 with feedback diode D4. Now I have to discuss it for rectification mode of operation and inversion mode of operation, because this is a single phase bidirectional boost converter. Bidirectional boost converter means it will operate in first quadrant and second quadrant. I mean, it can operate in rectification mode of operation, whereby energy flows from source to load, and it can operate in inversion mode of operation, where energy can flow from load to source, provided of course your load is an active load. Although I have not shown here active load, it can be a motor, DC motor load also. I will show in general here load. Okay, let us first of all discuss rectification mode of operation. Rectification mode. In the rectification mode, power flow should be from AC source to DC load. I mean, if your load is a motor, it should receive power from source and work as a motor. Power should flow from source to load. Okay, now you have positive half cycle and you have negative half cycle. Now, positive half cycle of source voltage. And there is positive half cycle of source voltage like this, 0 to pi. This terminal is positive with respect to this. This is A and this is B. What your controller will do, maybe a hysteresis current controller, HCC, it will issue control pulses to S2, S4 pair, not S1, S3 pair. S2, S4 pair of switches will be turned on. S2 and S4. When S2 and S4 is turned on, the capacitor is already positive, negative, and capacitor will supply energy. I mean, capacitor will discharge like this through S2, then current will flow like this through inductor, and then through S4 it will go back to the capacitor. Let me draw the equivalent circuit. It will be clear to you. Equivalent circuit. S2, and this is positive half cycle of source voltage. This is terminal B. S2 is conducting, तो आपका S2 ऑन हो रहा है और ये आपका आउटपुट कैपेसिटर है प्लस माइनस C और इसके अक्रॉस लोड रेजिस्टेंस R है. Okay, so current will flow like this. Then ये boost इंडक्टर के थ्रू ऐसे फ्लो होगी सोर्स करंट, and then it will flow through S4 back to source. ये आपका S4 भी conduct करेगा और back to source. So I repeat, current will flow, I mean capacitor will discharge slightly like this. I say. So current through the inductor, I mean this is energy storage interval 0 to dTs. Since current is flowing through the inductor like this, so energy gets stored in the inductor और ये inductor के through current बढ़ जाएगी. I mean source current will increase. If this is 0, this is pi, current will increase. And by the way, if this is this is terminal A, this is terminal B. You can see A is connected to negative terminal of the capacitor and B is connected to positive terminal of the capacitor. So what is VAB? A negative voltage pulse will appear across A and B. That's called converter input voltage negative हो जाएगी. And current through the inductor, which is the source current, rises. As soon as, I mean, if you are using hysteresis current control technique, as soon as this current touches the upper hysteresis band, this pair of switch will be turned off by your hysteresis current controller. So दोनों switch off हो जाएंगे, तो energy transfer interval शुरू हो जाएगा. ओके, एनर्जी ट्रांसफर इंटरवल शुरू हो जाएगा, वो मैं यहाँ लिखूंगा. एनर्जी ट्रांसफर इंटरवल मीन्स dTs to Ts. S2, S4 both switches will be off. S2 is off, S4 is off. इंडक्टर को एनर्जी रिलीज करनी है. अब पहले इसने एनर्जी स्टोर की थी, अब इसको रिलीज करनी है. व्हाट इज द पाथ? द करंट हैज टू पाथ्स. आई मीन व्हेन इट रिलीजेस द एनर्जी, इट हैज टू पाथ्स, आइदर D1 के थ्रू या S4 के थ्रू. S4 तो ऑलरेडी आपने आपके कंट्रोलर ने ऑफ किया, सो देयर इज नो पाथ डाउनवर्ड्स, बट देयर इज अ पाथ अपवर्ड्स. सो करंट विल फ्लो थ्रू डायोड D1, आउटपुट स्टेज में करंट फ्लो होगी, और D3 के थ्रू करंट वापस आएगी. इक्विवेलेंट सर्किट विल लुक लाइक दिस. आई विल राइट हियर इक्विवेलेंट सर्किट. आपका इक्विवेलेंट सर्किट कन्वर्टर का ऐसे दिखेगा. दिस इज इंडक्टेंस, दिस इज सोर्स करंट. Its inductor is now releasing energy through diode D1. D1 is conducting, and then this is the output stage. ये आपका terminal A है. Output stage ये है capacitor, and some energy goes into capacitor and some is consumed by the load. और यहाँ D3 के through वापस आएगी. ये terminal B है. So inductor will release energy like this. Now A is connected to positive terminal and B negative, तो converter input voltage positive हो जाएगी ऐसे. And what will happen to the current? Since inductor is releasing the energy against a high voltage, current will decrease. तो current क्या होगी? Decrease होगी. And as soon as it touches the lower hysteresis band, S2 S4 फिर से on हो जाएंगे, फिर से energy storage interval आ जाएगा, फिर से converter voltage negative positive ऐसे हो जाएगी. It will be something like this. एंड आपकी करंट इस तरह, दिस इज व्हाट विल हैपन टू द करंट. और आपका हिस्टेरेसिस बैंड, अगर हिस्टेरेसिस करंट कंट्रोलर का बहुत छोटा है, तो आपकी करंट ऑलमोस्ट प्योरली साइनोसॉइडल बन जाएगी, ये रिपल्स नहीं दिखेंगे. दिस इज व्हाट विल हैपन इन द पॉजिटिव हाफ साइकिल ऑफ सोर्स वोल्टेज. लेट अस सी व्हाट हैपेंस इन द ड्यूरिंग द नेगेटिव हाफ साइकिल ऑफ सोर्स वोल्टेज. नेगेटिव half cycle of source voltage. Negative half cycle of source voltage means this is plus, this is minus. Okay. And in the negative half cycle of source voltage, obviously current भी negative हो जाएगी, reverse हो जाएगी, होनी भी चाहिए. So what is the pair of devices which should be given control pulses? Your hysteresis current controller will not give now control pulses to S2, S4. It will give control pulses to a complementary pair of switches, S1, S3. S1, S3. S1, S3 will be turned on. Simultaneously, hysteresis current controller will issue control pulses to S1, S3. दोनों on हो जाएंगे. और आप देखिए कैपेसिटर इस तरह डिस्चार्ज करेगा through S1, S4 वापस. So equivalent circuit will look like this. Very interestingly, you can see now the negative half cycle of source voltage. यह आपकी इंडक्टेंस है, S1 ऑन हो रहा है, ये A है, टर्मिनल A. ये कैपेसिटर है जो डिस्चार्ज करेगा, और ये S3 है, S3 भी ऑन हो जाएगा, और ये टर्मिनल B है. This is load resistance. So capacitor will discharge through S1 और current ऐसे flow होगी और वापस. And that means energy will get stored in the inductor. This is energy storage interval, 0 to T to dTs. Energy storage interval. Now A is getting connected to positive, B is getting connected to negative. तो एक negative half cycle में पहली voltage pulse जो आएगी वो positive आएगी converter के. In those terminals, input across the input terminals of the converter, positive converter voltage will be there, voltage pulse of course. And what will happen to inductor? Inductor capacitor जो energy देता है वो inductor store करता है. This is energy storage interval. So current will increase during energy storage interval. Current through the inductor will increase, but since the source current is negative, so ये negative direction में increase हो जाएगी. तो इसका मतलब अगर ये hysteresis band है, ये negative direction में increase हो जाएगी. As soon as it touches the higher band, your hysteresis current controller will draw control pulses from both S1 and S3, and inductor will now release the energy. So उसके बाद आपका एनर्जी ट्रांसफर इंटरवल आएगा dTs to Ts. During this period S1 S3 pair of switches will be turned off. जब ये ऑफ हो जाएंगे, इंडक्टर हैज टू रिलीज एनर्जी. ये वोल्टेज अक्रॉस इंडक्टर है. व्हाट इज द पाथ फॉर एनर्जी टू रिलीज? D2, इट कैन नॉट फ्लो थ्रू S3 क्योंकि S3 ऑलरेडी ऑफ हो गया. दूसरा पाथ है D2. सो ये ऐसे एनर्जी रिलीज करेगा इंडक्टर. ये देखिए ऐसे B D2 के थ्रू D2, and some of the energy will go into the capacitor, will charge the capacitor, and rest of the energy will be consumed by the load. और रिटर्न पाथ कहाँ से होगा? थ्रू D4 के थ्रू वापस D4. यह आपका टर्मिनल A है. So inductor will release energy like this, D2 and back. अब A नेगेटिव के साथ कनेक्ट हो रहा है, B पॉजिटिव के साथ, तो नेगेटिव वोल्टेज आ जाएगी. उसके बाद कन्वर्टर वोल्टेज ऐसे आएगी, कन्वर्टर इनपुट वोल्टेज. इसको हम V कन्वर्टर भी कह सकते हैं. V कन्वर्टर मीन्स इनपुट वोल्टेज एट द इनपुट बूस्ट. इंडक्टर के बाद जो ये दो टर्मिनल आते हैं को इनपुट टर्मिनल्स कहते हैं कन्वर्टर के. सो दिस वोल्टेज इज कॉल्ड V कन्वर्टर. इट विल बी पल्स्ड लाइक दिस. अगर इसका फंडामेंटल कंपोनेंट निकालोगे, फंडामेंटल कंपोनेंट कुछ ऐसे होगा. सो देयर विल बी ऑलवेज अ फेज एंगल बिटवीन सोर्स वोल्टेज एंड कन्वर्टर वोल्टेज, डेल्टा, एंड दिस डेल्टा विल डिटरमाइन power direction of power flow. If Vs is leading V converter, then power will flow from source to load. Anyway, that's we'll discuss that later on. So now when inductor is releasing the energy against a higher voltage like this, what will happen to the current will decrease. Current decrease हो जाएगी और यह लोअर हिस्टेरेसिस बैंड को टच करेगी. जो ही ये लोअर हिस्टेरेसिस बैंड को टच करेगी उसके बाद फिर से S1 S3 पेयर ऑन हो जाएंगे और ये करंट विल फ्लो लाइक दिस 2 pi like this. So this is your source current and it will be in phase with the voltage. You can see just sinusoidal. मैंने यहाँ ज़्यादा रिपल्स दिखाए हैं लेकिन एक्चुअली इतने रिपल्स होते नहीं. रिपल्स इतने छोटे होते हैं दैट यू कैन नॉट मेक देम आउट, यू कैन नॉट सी देम unless you zoom a portion of the waveform. And this source current is nearly sinusoidal and in phase with the voltage. This is for rectification mode of operation. Why is this rectification mode of operation? Because you can see source voltage is positive, source current is also positive. So source power, which is the product of source voltage and source current, is positive. Positive means there is flow of power from source to load. Source से load की तरफ power जा रहा है. Power is flowing in this direction from source to load. Let us see how we can achieve inversion mode of operation. Now, part B is, case B is inversion mode of operation. In inversion mode of operation, if this is your source voltage, for example, 0, pi, 2 pi, source current should be 180 degrees out of phase with source voltage, so that source power, which is the product of voltage and current, since voltage is positive, current is negative, so power is negative. Negative power means source is not delivering the power, it is receiving power. That means power is flowing in the reverse direction from load to source. How to achieve this? Let us see. इसमें भी हम पहले पॉजिटिव हाफ साइकिल सोर्स वोल्टेज का लेंगे. First of all, take positive half cycle of source voltage Vs. When we have positive half cycle of source voltage, plus minus like this, your controller, hysteresis current controller, rectification mode में वो positive half cycle में S2 S4 को on करता था, फिर off, then again on, then off. पॉजिटिव हाफ साइकिल में. नेगेटिव हाफ साइकिल में इस पेयर को ऑन ऑफ करता था. लेकिन इन्वर्शन मोड ऑफ ऑपरेशन में इट इज जस्ट रिवर्स. इन्वर्शन मोड ऑफ ऑपरेशन में इट विल नॉट टर्न ऑन एंड ऑफ S2 S4, इट विल टर्न ऑन एंड ऑफ S1 S3. So S1 S3 pair will be simultaneously given control pulses, both of them will turn on. So when S1, S3 are turning on, we can see capacitor is releasing energy through S1, then through S4. So let me draw the equivalent circuit. You will be able to understand its operation. Equivalent circuit will be like this. Source voltage is no doubt positive. This is the inductor. Since S1 is conducting like this, और then ये आपका कैपेसिटर है C, ये लोड है. S3 is also conducting. So how will the current flow? Current will flow from capacitor to source. So capacitor will slightly discharge. It will flow in this direction. So source current negative हो जाएगी और source current rise हो जाएगी. मैं यहाँ पे दिखा सकता हूँ. I mean, if this is source voltage, positive half cycle में, if this is source voltage, source current negative जाएगी और positive, and it will rise. और ये आपका energy storage interval है, 0 to dts. As soon as this current touches the upper hysteresis band in the negative half cycle, I mean when current is negative, the hysteresis current controller will turn off both the devices, S1, S3. So S1, S3 will be turned off. And there will be transfer of energy from inductor to output stage. So dts to ts, that is energy transfer interval. So during this interval, S1, S3, both switches will be turned off. When S1 is off, S3 is off, inductor के across ये voltage है, so inductor will try to release the energy. तो energy ऐसे release करेगा, जब ऐसे release करेगा, S3 के through तो flow नहीं हो सकती current, because S3 you have already turned off. D4 के through flow होगी, and then return D2 के through flow होगी, and return path will be provided by D4. So it is like this. Minus plus source voltage positive है, plus and minus. This is the inductor. Inductor is now releasing the energy. Okay, when it is releasing the energy, D2 will conduct. I can show you here. D2, then current will flow into the output stage C, some current into the capacitor, and rest of the current in the load resistor R, and return path will be provided by D4. So inductor will release energy like this through D2, energy output stage में जाएगी, and return path. So what will happen to the current through the inductor? It will decrease, and as soon as it touches the lower hysteresis band, then again S1, S3 will be on. There will be again energy storage interval, energy transfer interval, till the cycle gets complete, 0 to pi. This is what happens during positive half cycle. Therefore, during positive half cycle of source voltage, your hysteresis current controller should issue control pulses at a switching frequency to this pair of devices. S1, S3 on, then off, then again on, then off. Energy storage interval followed by energy transfer interval. Then again energy storage interval, energy transfer interval, and your actual source current will follow the reference current within narrow hysteresis band like this, and it will be purely sinusoidal in nature. This is what happens during positive half cycle of source voltage. Let us see what happens during the negative half cycle of source voltage. Negative half cycle of source voltage. Negative half cycle of source voltage means this terminal is positive with respect to this. Now the other pair of devices will be conducted. S2, S4 pair will be turned on by your hysteresis current controller. As soon as it turns S2 and S4 pair on करता है इनको, what happens? The current will flow through S2 and then through S4 like this. So let me draw the equivalent circuit. It will be clear. अब नेगेटिव हाफ साइकिल है सोर्स वोल्टेज का, प्लस माइनस लाइक दिस. S2 ऑन है, ये S2 आपका ऑन है, S2, and it is connected to capacitor. Let me first of all draw, then I will explain. Resistor and S4 भी ऑन है. So capacitor will discharge like this. देखिए capacitor discharge करेगा ऐसे, then current will flow through the inductor like this, return path. So since current is positive, half cycle is negative. आपकी सोर्स वोल्टेज का नेगेटिव हाफ साइकिल है, ये देखिए पाई टू 2 पाई, लेकिन करंट पॉजिटिव हो रही है. It is rising as soon as it touches the upper hysteresis band. As to inductor, energy gets stored in the inductor, energy storage interval. As soon as this current touches the upper hysteresis band, this pair of devices is turned off. S2, S4 is turned off. Let me show you during energy transfer interval now. S2, S4 devices is turned off. अब इस इंडक्टर को एनर्जी रिलीज करनी है. यह टर्मिनल पॉजिटिव होगा इस टर्मिनल के विद रिस्पेक्ट, सो D1 और D3 कंडक्ट करेंगे. सो इट विल बी समथिंग लाइक दिस. लेट मी शो यू वेरी इंटरेस्टिंगली. इंडक्टर हैज टू रिलीज एनर्जी. ये टर्मिनल इंडक्टर का पॉजिटिव हो जाएगा, ये नेगेटिव, बिकॉज करंट इज इन दिस डायरेक्शन. इट हैज टू रिलीज द एनर्जी. व्हेन इट रिलीजेस द एनर्जी, करंट कैन नॉट फ्लो थ्रू S4 क्योंकि S4 आपने ऑफ किया है. द ओनली पाथ फॉर द करंट इज टू फ्लो थ्रू D1. Flow through D1, then into the output stage. Some of this current will be dumped into the capacitor and it will charge the capacitor, and some will flow into the load as load current. और जब ये वापस आएगी, current will flow through D3 back. So inductor releases energy like this. Since this current has to flow through a high voltage, इंडक्टर रिलीजेस द एनर्जी. ड्यूरिंग एनर्जी रिलीज इंटरवल करंट फॉल्स, तो करंट फॉल हो जाएगी. जो ही ये लोअर हिस्टेरेसिस बैंड को टच करेगी, फिर से एनर्जी स्टोरेज इंटरवल शुरू हो जाएगा. S2, S4 फिर से ऑन होगा, एंड अल्टीमेटली यू विल गेट दिस टाइप ऑफ करंट. दिस इज योर सोर्स करंट. ओके, so therefore your source current is 180 degrees out of phase with source voltage. And what is your source power? It is RMS value of source voltage into RMS value of source current. Since source current is negative with respect to voltage, so it is minus IS, so it is negative. So negative means source is not delivering power to the load, rather it is receiving power from the load. So therefore power is now flowing from load to source. So this explains inversion mode of operation of boost converter. This is how bidirectional boost converter delivers energy in both the directions. How it operates in rectification mode of operation and delivers energy from source to load, and then how it operates in inversion mode of operation and delivers energy from load to source. So it can be like this. I mean, in one waveform you can show this. I mean, if this is your source voltage, your source current is 0, pi, 2 pi, 3 pi and so on. Source current is first positive, and then suppose inversion takes place here, then source current becomes negative. यहाँ से यहाँ तक source voltage and source current both are positive and in phase. So this is rectification mode of operation. इस point के बाद source voltage और source current 180 degrees out of phase हो जाती है. Inversion mode of operation. So this rectification to inversion mode you can do at any instant of time depending upon the requirement. So whether your converter is operating in rectification mode of operation or inversion mode of operation, the current drawn by it is purely sinusoidal, and input power factor is unity, which is near unity. Unity means 1.0. So therefore your single phase bidirectional boost converter also appears as a linear load to your source. The grid or the source sees it as a linear load, drawing purely sinusoidal current without harmonic distortion, and no reactive power is drawn by load from the source because input power factor is unity, current is in phase with the voltage. So this explains the operation of single phase bidirectional boost converter. In today's lecture we have discussed single phase unidirectional boost converter, two topologies, in continuous conduction mode, and then single phase bidirectional boost converter also in continuous conduction mode. In continuous conduction mode, the pulse width modulation or PWM technique that we use generally is hysteresis current control, HCC technique. And for the current is continuous, it is not discontinuous. You don't need any input filter. But for achieving this sinusoidal current, you need a closed loop system, and current loops are also required. Whereas if the same converter is operating in discontinuous conduction mode of operation, the current will not be continuous, it will be discontinuous like this. That means if this is your source voltage, source current will be in the form of pulses like this, and then you need a filter to filter out the high frequency harmonics in this current and make current sinusoidal. But in continuous conduction mode of operation using hysteresis current control technique, you don't, the current, since current is programmed using current loop, it is continuous, it's not discontinuous in the form of pulses, and it is almost purely sinusoidal. You don't need any input filter. Okay, then I also told you that when you use hysteresis current control technique, when you use boost converter, the boost converter should always be used in closed loop control. It should not be used in open loop, because in open loop there is a danger of dangerously high voltage, load getting dangerously high voltage, because if load suddenly drops, it's turned off, and your converter is operating in open loop, then there will be continuous transfer of energy from source to load, and since load is disconnected, this energy will get dumped into the capacitor, it will keep on raising the capacitor voltage until a very high voltage will appear across the load. That may damage your devices, and that may be very dangerous for the operating personnel also. So therefore, to avoid such a situation, the boost converters should always be operated in closed loop operation. In closed loop operation, there is a voltage feedback loop, and the load voltage is always compared with reference load voltage, and whenever you find that load voltage has increased, a negative error will be produced by voltage feedback loop. Accordingly, less energy will be drawn from the source. So it will prevent the load voltage to go to very high values. So this is all about various types of improved power quality AC to DC converters. Mostly I have discussed with you single phase improved power quality AC to DC converters. The same logic applies to three phase improved power quality AC to DC converters. And we have studied single phase unidirectional AC to DC converters, in which I have told you, in discontinuous conduction mode first, in which I have told you that whenever a DC to DC converter operating in discontinuous conduction mode is connected to a rectified AC line, it gives self power factor correction property. And we have displayed that property in last to last lecture. We have discussed various types of single phase improved power quality AC to DC converters operating in discontinuous conduction mode with self PFC property. The various types of converters we have discussed were single phase unidirectional AC to DC buck converter, single phase unidirectional AC to DC boost converter, then buck boost converter, and then flyback converter. And then we discussed single phase pulse width modulated PWM AC to DC converter, which is basically a single phase bidirectional buck converter. And in today's lecture, we discuss single phase unidirectional boost converter and single phase bidirectional boost converter, but in continuous conduction mode of operation using hysteresis current control mode, that is HCC technique. So this gives an overview of various types of improved power quality AC to DC converters, and these improved power quality AC to DC converters are a new trend. Wherever new installations are constructed or designed, it is preferred that improved power quality AC to DC converters be installed there, because they will act as linear load on the system. They will not cause harmonic distortion, and they will not draw any reactive power from the source. But in old installations where already traditional or conventional phase controlled or diode bridge rectifiers are there, it will be very costly if you are to replace them by improved power quality AC to DC converters. There we use passive filters or active power filters for power factor, for power quality improvement. But in new installations, the modern trend is to use improved power quality AC to DC converters. These improved power quality AC to DC converters act as linear loads, and they are a new breed or new generation of AC to DC power converters. They have already gained a widespread popularity in single phase applications, and now they are taking up in three phase applications also. So this completes our discussions on AC to DC, improved power quality AC to DC converters. And with this, this is the end of lecture number 42. And I am very pleased to declare the end of the syllabus of our beautiful course, very informative course on power quality problems and solutions. If I summarize what we have discussed over the last 42 lectures in a few words or few sentences, we started with introductory part where I discussed with you what the definition of power quality, the meaning of power quality, what is power quality, and what are power quality problems, and how these power quality problems have become, headache and a cause of concern for industries and power system and power electronics engineers in modern era. And what are the various drawbacks of the various types of power quality problems like harmonic injection, large reactive power, voltage dip, that's voltage sag, voltage swell, voltage flicker, transients, and these voltage fluctuations, voltage flickering, and so on. How they result in loss of labor, loss of time, loss of raw material, loss of revenue, and how they result in loss of billions of dollars, millions of dollars every year in developed countries and also in developing countries. Now, to address those power quality problems, I discussed with you briefly what we do. We use custom power devices. Custom power devices are power electronics based, these converters, power electronics converter based solutions which ensure a reliable and high quality of power being fed to the load. There are various types of loads which are themselves responsible for creating various types of power quality problems, like your load may be a nonlinear load and it may draw distorted currents which may result in voltage distortions at the point of common coupling. Your load may be a three-phase unbalanced load and it may draw unbalanced line currents causing unbalanced voltages at the point of common coupling. And when those unbalanced voltages are fed to voltage sensitive loads like three-phase AC motors, the AC motors give more losses, extra losses, less efficiency, and other problems like torque, pulsations, vibrations, and so on. And harmonics themselves, they create, they produce distorted voltages at the point of common coupling, and those distorted voltages when fed to voltage sensitive loads like medical equipment and other voltage sensitive loads, those voltage sensitive loads start maloperating. They don't operate satisfactorily. Okay, so therefore, to address the power quality problems, I discussed with you various techniques. First, we discussed passive techniques and then active techniques. In passive compensation, first of all, I discussed how to compensate various types of power quality problem producing loads. Various distorting loads like three-phase unbalanced loads, non-linear loads, single-phase non-linear loads, how to compensate such type of loads, how to compensate reactive power, how to compensate harmonics, and how to compensate unbalance in loads using passive compensation. A large number of lectures were dedicated to that discussion. That was followed by active compensation using, active devices like custom power devices. Like for load compensation, I discussed with you DStatCom, and for source voltage compensation, I discussed with you dynamic voltage restorer DVR. And for addressing both voltage related as well as current related power quality problems, we use unified power quality conditioners, UPQCs. And if you require your custom power devices or voltage source inverters primarily for filtering purposes, for filtration of harmonics in the load currents or for filtration of harmonics in the source voltages, then they are called shunt active power filters, series active power filters, and hybrid power filters. We have discussed that part also. First of all, passive filters we can use, and then we can use active power filters or combination of both, which gives hybrid power filters. And then the last module was dedicated to these filters, passive and active power filters, and improved power quality converters. I mean, if you don't want any nonlinear load, if you don't want any current related power quality problem, no current harmonics, no reactive power, large reactive power flow, no load unbalancing, then it is better to use improved power quality AC to DC converters, which will act as linear loads on the system. And over last 3 lectures, we have been discussing various topologies and operation of various types of improved power quality AC to DC converters. So therefore, using custom power devices and IPQCs, that's improved power quality AC to DC converters, will solve power quality problems to a very large extent. So this is a very beautiful course. I have already told you that in many internationally reputed universities and many foreign universities, they have separate research wings for power quality, where the faculty and researchers are dedicating their research to power quality itself. In India also, in many IITs, a lot of research work is being done in this area, because this is an upcoming area. This is power quality problems are burning issues, and we as academicians and researchers can play a very important role in suggesting solutions to the industries, to the electric utilities, for addressing various types of power quality problems. I hope that over last 3.5 months, we have been discussing this subject exhaustively. I hope it will at least form the foundation for you to understand what power quality is, what are various types of power quality problems, and how we can provide solution to these various types of power quality problems. I wish that in future some of you take take power quality as their research problems and work in this area and suggest some very good or improved solutions for these power quality problems. So I will end my today's lecture, and I again declare the course closed, the syllabus closed. The syllabus of this course is already over. I advise all of you to go through these lectures and don't study this subject only from examination point of view. Study it from the point of view of learning various techniques, the various aspects of this subject. I wish all the best to you for upcoming exams. I hope you will perform well in the exam, and I hope that you will study this subject very well even after your exams are closed. Your exams are over. You will get 1 or 2 months winter break, winter vacations. You can go through this subject again, and you can use MATLAB software or any other software, simulate various types of these converters, and you can take various types of these power quality related problems, do the exhaustive simulation, and you can learn a lot from those simulations. I again thank all of you for being patient and for your cooperation, for watching these video lectures, for giving your feedback, and for showing interest in the subject. I wish all the best to all of you again. Thank you very much.